Hello, welcome to another module in this massive open online course. So we are looking at examples to understand the mathematical preliminaries of optimization. Let us look at another example, and this is something that's very important and has a lot of practical utility. This is termed as the Gram-Schmidt orthonormalization process. Okay. So we are looking at examples, correct? And as part of the second example, what we want to look at is the Gram-Schmidt procedure for orthonormalization. Gram-Schmidt procedure for orthonormalization. And what this does is, for a given set of linearly independent vectors u1 bar, u2 bar, un bar. So, this is a set of linearly given set of linearly independent vectors. What the Gram-Schmidt orthonormalization procedure does is it creates an orthonormal set, I am just going to explain in a moment what this means. It creates an orthonormal set of vectors that span the same subspace, subspace in the sense that linear combinations of these vectors can be used to generate any vector in that subspace. Alright. So, both these subspaces spanned by these sets are the same. And what is the meaning of this term orthonormal? An orthonormal set of vectors is a set in which each vector has unit norm, that is the normal, right. We said the process of making the norm of vector unity is normalization, and orthogonal represents the fact that the vectors in this set, all the vectors in this set are pairwise orthogonal to each other. So, that makes it an orthonormal set of vectors. Okay. So, we have an orthonormal basis which is frequently very convenient to consider for as the basis of a vector space. So, V1 bar, V2 bar, Vn bar. Now, this is orthonormal implies norm Vi bar, each vector norm Vi bar equals to 1. This is basically your normal property, and if you look at any pairs of vectors Vi bar Hermitian, or if they are real vectors Vi bar transpose Vj bar equal to 0 if I naught, or for all I naught equal to j, for any I naught equal to j. Alright, and this basically represents the orthogonal property. So, they are orthonormal in the sense all the vectors in the set are orthogonal to each other and each vector has unit norm, alright, and they span the same subspace. So, how does this procedure work? Well, the procedure works in various steps, the Gram-Schmidt orthonormalization procedure, and that can be described as follows. Okay. So, what we do is we start with the first vector. In the first step, you can think of this as step 1. What we do is we create a unit norm vector, that is we create first V1 bar equals U1 bar divide. So, at each step we create a set of orthonormal vectors. So, the first step is we create a vector V1 bar equals U1 bar divided by norm U1 bar. So, you can observe that this is unit norm, because in fact what we are doing is we are normalizing vector U1 bar by its norm. So, this is unit norm. Okay. So, that is implies norm V1 bar equals 1, so far satisfies the criterion for Gram-Schmidt orthonormalization. Now, in step 2, what we do is we want to create a vector that is orthogonal to V1 bar. Remember, so we look at V2 tilde equals U2 bar minus, what we do is we subtract the projection of U2 bar on V1 bar. That is what we are doing. And so, what we are doing here is we are subtracting projection of U2 bar on V1 bar. That is, we have these two vectors, remember, let us say this is V1 bar, and now you have this vector U2 bar, and this can be represented as the sum of two components. One is the projection, which we can term as the parallel component, U2 bar the parallel component, you can write as U2 bar P, and the other is the perpendicular component, and this can be written as U2 bar perp. So, what we are doing is we are subtracting this component along V1 to create something that is parallel to V1 bar. So, subtracting and retaining whatever is perpendicular to V1 bar, that creates basically the orthogonality property. Okay, and that is what the Gram-Schmidt orthonormalization procedure is achieving. Okay, and of course, now we have to ensure unit norm. So, now V2 bar equals V2 tilde divided by norm of V2 tilde, and this makes it unit norm. Okay. And you can see orthogonality as follows. Consider just a quick demonstration of orthogonality. Consider V2 bar, we are already seen V2 bar is unit norm, V2 bar transpose V1 bar equals V2 tilde transpose divided by norm V2 tilde times V1 bar, because V2 bar equals V2 tilde divided by norm V2 tilde, something that we have already just seen. Now, this is 1 over norm V2 tilde times, well, V2 tilde is nothing but what we have seen, V2 tilde transpose is, well, as we just seen, that is U2 transpose, U2 bar transpose minus U2 bar V1 bar inner product into V1 bar transpose times V1 bar. Now, if you expand this, what you obtain is this is norm of V2 tilde, U2 bar transpose V1 bar, that is the inner product of U2 bar comma V1 bar minus the inner product of U2 bar comma V1 bar times V1 bar transpose V1 bar is norm V1 bar square, but this is nothing but this is equal to 1. Since this is equal to 1 over norm V2 tilde times U2 bar V1 bar minus U2 bar V1 bar, which you can now see is basically nothing but this is equal to 0, implies V1 bar orthogonal to V2 bar, and this can also be represented as V1 bar perpendicular to V2 bar, because remember we said the cosine of the angle between these two vectors is related to the inner product. If the inner product is 0, angle, which means the cosine of the angle is 0, alright, which means the angle is theta is 90 degrees, and therefore the vectors are perpendicular to each other. Okay. And now, so basically now we have created V1 bar, V2 bar. So basically at every step we are creating a set of orthonormal vectors. Now at step 3 you can clearly see how we can generate. We have V3 tilde equals, well, U3 bar minus, remove the projection of U3 bar on V1 bar minus remove the projection of U3 bar on V2 bar. So this inner product is basically giving the projection on the unit norm vector. Okay. Inner product with the unit norm vector gives the projection. Okay. So these are basically projections on V1 bar comma V2 bar, and these are being subtracted, and now we create a unit norm vector by V3 bar equals V3 tilde divided by norm V3 tilde. So what this does is this creates a unit, this creates a unit norm vector. Okay. And now you can quickly check the orthogonality property once again. If you do V3 bar transpose V1 bar, let us say, or V3 bar transpose V2 bar, just to make sure it is orthogonal to the previous vector. So I have 1 over norm V3 tilde transpose V2 bar, this is 1 over V3 tilde norm times U3 bar minus U3 bar inner product V1 bar, of course this will all be transpose because you have to take the transpose, minus U3 bar comma V2 bar into V2 bar transpose whole times V2 bar. And now you can see this will be 1 over norm V3 tilde U3 bar transpose V2 bar equals U3 bar V2 bar inner product minus U3 bar V1 bar inner product into V1 bar transpose V2 equals 0. Okay, observe that V1 bar transpose V2 bar equal to 0, okay, into 0 minus U3 bar inner product V2 bar into V2 bar transpose V2 bar, that is norm V2 bar square, which is once again 1. So this is basically again 1 over norm V3 tilde U3 bar comma V2 bar minus inner product U3 bar V2 bar, which is equal to 0. This quantity is 0. So this implies, and you can similarly verify orthogonality of V3 bar to V1 bar as well. So this implies V1 bar, V2 bar, V3 bar is an orthonormal set, and this procedure can similarly be continued. Okay. So, we have V1 bar, V2 bar, V3 bar, this is an orthonormal set, and the procedure can be similarly continued. And the procedure can be similarly continued. And what we do in step n, if you look at the nth step, correct, in step n what we do is we have Vn tilde, this will be Un bar minus Un bar comma V1 bar into V1 bar minus projection of U1 bar on V2 bar, remove that, V2 bar minus so on so forth. Last one is you remove the projection along V n minus 1, remove the projection along n minus 1 bar. Okay. And finally, we have Vn bar Vn tilde divided by norm Vn tilde, okay, and this generates the unit norm. Remember, the orthogonality property is not affected by the norm. So, all we have to do is take the vector and simply divide by its magnitude to get the divide by the norm to get the corresponding unit norm vector. Okay, that basically summarizes the Gram-Schmidt orthonormalization procedure. Let us look at a specific instance of this procedure, application of this procedure, considering a set of vectors to demonstrate how this procedure actually works in practice. Okay. So, this is, you can think of this as an example inside an example, you can think of this as an illustration, a practical illustration of the Gram-Schmidt orthonormalization procedure. So, consider three vectors, that is U1 bar, that is the vector 1 1 minus 2, U2 bar equals the vector 1 2 minus 3, and U3 bar equals the vector 0 1 1. And now we have V1 bar equals U1 bar divided by norm U1 bar. Now observe that norm U1 bar equals square root of, well, 1 square plus 1 square plus 2 square equals square root of 6. So, this V1 bar equals 1 over square root of 6 times 1 1 minus 2. So, this is your unit norm vector. Okay. Observe that this is a unit norm vector. This is the first step. Step 1, we do not remove any projection because there is no vector in the set V bar yet. Okay. Remember, we have to remove the projections on the previously chosen vectors V1 bar, V2 bar, Vn minus 1 bar at step n minus 1. So, step 2 onwards we remove the projections. So, that is V2 tilde equals your U2 bar minus the projection of U2 bar on V1 bar, which is given by this inner product, since V1 bar is a unit norm vector, and this is basically 1 2 1 2. So, U2 bar is 1 2 minus 3, the vector 1 2 minus 3 minus, you can check the inner product, U2 bar transpose V1 bar is 9 over square root of 6 times 1 over square root of 6 into 1 1 minus 2, and this will basically be so V2 tilde is minus half comma 0, and norm of V2 tilde is square root of 1 by 4 plus 1 by 4 plus 0, that is square root of half, that is 1 over root 2. So, V2 bar equals V2 tilde divided by norm of V2 tilde. This is basically your 1 over square root of 2. So, square root of 2 times minus half 0, taking the factor of half outside, this becomes 1 over square root of 2 times minus 1 1 0, and you can clearly see this is a unit norm vector, and you can also see this will be orthogonal to V1 bar. So, V2 bar transpose V1 bar is, well, 1 over square root of 2 minus 1 1 0 times 1 over square root of 6 times 1 over square root of 6 times 1 1 minus 2, and you can clearly see this is minus 1 plus 1, which is 0, plus 0, which is 0. So, 1 over square root of 12 times 0, so this is 0. Okay. So, implies these are orthogonal, that is V2 bar perpendicular to V1 bar, or the same thing as saying V2 bar V1 bar or orthogonal. Okay. So, that completes your step 2. First, remove the projection of V1 bar from U2 bar and then divide by its norm, that is you obtain V2 tilde, divide by the norm of V2 tilde to obtain the normal vector. Alright, and V2 bar you can see is also orthogonal to V1 bar, therefore, it makes it an orthonormal set. Now, step 3 is again similar, very similar. So, U3 bar minus U3 bar projection along V1 bar into V1 bar minus U3 bar V2 bar inner product to V2 bar, and this will be, you can check, this is U3 bar is, we have seen this is given 0 1 1, this is the vector 0 1 1 minus the projection, the inner product is minus 1 over square root of 6 times 1 over square root of 6 times 1 1 minus 2, that is your V1 bar, minus 1 over square root of 2, that is a projection, 1 over square root of 2 times minus 1 1 0, all right. So, and that will be basically, if you can simplify this, this will be 0 1 1 plus 1 over 6 1 1 minus 2 minus 1 over 2 minus 1 1 0. So, this will be 0 plus 1 by 6. So, if you look at this 0 plus 1 by 6, that is half. So, half plus 1 by 6, half plus 1 by 6, that is 4 by 6. So, this will be 2 by 3. You can also check second entry will also be 2 by 3 and third entry will also be 2 by 3. So, that is 2 by 3 into 1 1 1 and norm, and this is basically your V3 tilde, okay. And norm of V3 tilde you can also compute that very easily, that is square root of, well, that will be 4 by 9 into 3, 4 by 9 plus 4 by 9 plus 4 by 9, that will be 2 by 3 square root of 3, and therefore, finally, V3 bar equals V3 tilde divided by norm V3 tilde equals, well, 2 by 3 1 1 1 divided by the norm into 1 over 2 by 3 square root of 3, and that will be equal to, well, 1 over square root of 3 times 1 1 1. So, finally, we have the orthonormal set of vectors which span the same space as u1 bar, u2 bar, u3 bar, remind you. So, this is 1 over square root of 6 1 1 minus 2 v2 bar equals 1 over square root of 2, apologize, 1 over square root of 2 minus 1 1 0, and V3 bar equals 1 over square root of 3, and this is 1 1 1. This is your orthonormal set of vectors V, okay. And you can once again check, if you do V3 bar transpose V1 bar, just do a quick check, that would be V3 bar transpose V1 bar. So, that would be, well, 1 over square root of 3 times 1 1 1 the row vector times 1 over square root of 6 times 1 1 minus 2, which is basically 1 plus 1 minus 2 divided by square root of 18, and you can see this is equal to 0. And therefore, V1 bar, V2 bar, and you can similarly check for the inner product or V2 or V3 bar transpose V2 bar. In fact, you can readily see that they are also orthogonal, therefore, V1 bar, V2 bar, V3 bar is an orthonormal set. And remember, the important thing about this is they span the same subspace as the original vectors U1 bar, U2 bar, U3 bar. So, that is the connection between this set, the new set V and the old set U bar. And several times it is very convenient to represent to find out an orthonormal span. So, although both the given sets span the same subspace, it is very convenient to deal with V rather than U, because V is an orthonormal set of vectors that spans the same subspace. And in fact, this can be used to not only find the orthonormal span for a vector subspace, remember this can be used for any inner product space, alright. And we have already said that the set of functions, for instance, continuous functions, forms an inner product space, continuous functions on the interval a and b. So, given a set of basis functions, linearly independent functions on that, right, which spans subspace on that, one can similarly determine an orthonormal set of functions, that is functions which are orthogonal to each other and have unit norm and that span the same subspace of continuous functions on the interval a b. So, this Gram-Schmidt orthonormalization procedure is something that is very convenient, very handy, and it is very popular, or it is highly applicable in practice because of its first because it is a low complexity procedure, and two, it has immense utility in terms of simplifying either deriving the span of a subspace or the representation of a set of or representation of a new vector to represent it in this subspace can be much readily derived or much more easily derived using the orthonormal span for the same subspace. So, we will stop here and we will continue with other aspects in the subsequent modules. Thank you very much.